Hey everybody, welcome back. Today we're going to talk about Rayleigh Flow, or a lot of times people will, in the United States at least, will pronounce it Raleigh Flow. But it's which is it's very analogous to Fano Flow. So our development of it you'll see a lot of parallels between the two as we go through the relevant mathematics. The flow scenario is named after Lord Rayleigh, who is actually my fourth great grand advisor. A very important scientist from the late 19th and early 20th century. One of the early Nobel laureates, in fact, for isolating argon gas, I think. Something like that, something to do with argon. But he has all sorts of major contributions, like Rayleigh scattering, which is the mechanism that is responsible for the sky being blue. There's a really famous fluid-like instability called Rayleigh-Taylor and Rayleigh plateau. There's also Rayleigh waves, which are like surface solid waves. He also, laid the groundwork for quantum mechanics. As far as his personal life, he was, born to a very wealthy noble family that became wealthy in about 1810. He succeeded James Clerk Maxwell as in his professor seat position at Cambridge University. And he eventually became chancellor of that university and then president of the Royal Society. So just kind of a golden thread in his life of really good work and being in a position to share that work with the world. In my opinion, he's probably the most brilliant, noble person that I know of, a person that was born, exceedingly rich. He was very gifted. So it's a really interesting guy to have to be super independently wealthy and yet spend a lot of your time focused on science. So yeah, very, very, very productive life he had. But what Rayleigh flow is that it is flow with heat transfer. Very specifically, flow with heat transfer and everything else held constant. That's the Rayleigh flow condition. Okay, so very similar to Fano flow. We're going to isolate the heat transfer effect. Just like with Fano flow, we isolated the friction. So we will have the situation be steady, 1D. We'll have no work being done. We'll have no major potential changes, and we'll also have a constant area duct. Okay, and then we're also going to assume that the heat transfer rate is large, such that the component of entropy produced due to heat is much greater than the irreversible entropy produced to irreversibilities. So essentially what that means is that we can treat DSI as being approximately zero in this case, okay? So that's we can basically ignore the frictional effects. Okay, even if they do exist, we're assuming that they're negligible. And then it allows us also to essentially just express ds as dse, which you may remember can be set equal to delta q over t. And that has to do with that integrating factor that Clausius found for us in the first lecture. So we're going to start our analysis of this type of flow in the same way that we do all these different situations. We're going to start with continuity. So it's the exact same thing as Fano. Because dA was equal to 0 for Fano as well. And so we're going to end up with the mass velocity g being equal to rho v as a constant. Okay, so that's nice. If we look at conservation of energy, this is where we're going to see our first difference. So the energy equation tells us that the total enthalpy at state 1 plus the heat transfer is equal to the total enthalpy at state 2 plus any work done. Well, we know that there's no work being done, right? But now we have a heat transfer in the mix here. And this is very important. This is sort of the first major scenario that we're running into where the stagnation temperature, Tt, is not constant. Okay, so up to this point, you probably have almost gotten to the point, especially as you do your homework, where you consider this to almost be you just assume that the stagnation temperature is constant by default. But you need to be very careful with Rayleigh flow because it is not constant. Okay, and we move on to conservation of momentum. We'll sort of draw our little mini pipe section cut here. We have a little control volume with some flow in and flow out. We have downstream pressure and velocity and upstream pressure and velocity. And we're going to define this as the positive x direction. Okay, so then the pressure on the left and right of the control volume is the force due to pressure. If we sum those, we'll get P1A minus P2A, and that's going to be equal to the mass velocity GA, and that's just your m dot, right? Times V2 minus V1, so equal to the change in velocity from left to right. Okay, and like we said, we're going to consider those or ignore those friction effects. And so what this equation leads to is that this quantity P plus G V being the V being the velocity, is equal to a constant. Okay, it's like a new conserved quantity for Rayleigh flow. And we can actually rewrite this thing on the left as P plus G squared V, lowercase v, where v is the specific volume. Okay, and this quantity on the left, so this becomes like we'll plot lines of constant P plus G squared V when we write down a Rayleigh line, right? A lot of our analysis of Fano flow is centered around these thermodynamic process diagrams for Fano lines, and we're going to look at Rayleigh lines in much the same way. So we're going to plot a line of constant P plus g squared v. Okay, so that means essentially that if we're going to plot this line, p is going to go as, negative g squared times v. So it's like a negative slope linear line that we're going to plot here. Okay, so let's see here. Well, we're going to plot it on a PV diagram, of course. I'm going to draw this one a little bit bigger than normal. So the PV, okay, and we'll do this kind of straight line that looks like that. Okay, and what direction would this process go? Well, we're increasing heat, right? So if we're turning the heat up, adding heat between states 1 and 2, say, we would expect the pressure to go down and the volume to go up, right? We wouldn't expect the opposite to be happening as heat is being added. So just because we know how an ideal gas behaves. So we know that sorry, I'm trying to make sure that there's enough room on the plot. So I want to get the angle of this straight Rayleigh line just right. I wonder if I can actually just make a proper straight line here. Yeah, there we go. That'll be better. Okay, so there's our Rayleigh line. We'll say that we're starting here at state 1, and then we'll have an intermediate state, and then a state 3. Okay, so that'll be the 3 states that we'll consider to start. Okay, and then what we would like to do is we'd like to draw lines of constant temperature on this plot, right? And so we know that from the ideal gas law equation of state that PV is equal to RT, right? And so what that tells us, if T is constant, is that P is going to go as 1 over V for T const, right? So our lines of constant temperature are go as 1 over V. So they're shaped like this. It's just kind of help you work out how to draw these diagrams. Okay. Yeah, that's all right. That looks okay. I think that bottom one's a little flatter than I would like it to be. Okay. So these are lines of T constant. Okay. And of course, as T increases, you're going to be moving this way. Okay. T increasing. All right, so we can see that as the Rayleigh line progresses in this direction, we are moving towards higher temperatures, right? Which matches our intuition. We're adding heat, so we should be as we add heat to the flow, we should be seeing the temperature go up, right? But eventually, it does hit a maximum temperature at state 2 here, and you would think that would be something like a limiting point for this process. So is state 2 a limiting point? And as I alluded to, I putting up a third state on there. It's not. So this is a little unintuitive. But we need to go to our point of highest entropy. So the limiting point is point of highest entropy. And if we want to draw entropy on these lines, so if we're draw isentropes, we need to look at our polytropic process where P v to the gamma is equal to a constant, right? So then therefore P goes as 1 over v to the gamma, where gamma is strictly greater than 1, but it's always going to, in this case it's about 1.4, because we're usually dealing with air, right? So since gamma is greater than 1, the lines of constant entropy are a little bit steeper than the, and I'll just kind of dash them in here. They're steeper than the lines of constant temperature. Kind of look like this. Okay, so this is an S constant line. And then, like with temperature, S increases in that direction. Okay. So we can see that the way I've drawn it here. In fact, I was a little messy at the end here. But the way I've drawn it, you can see that the Rayleigh line is hitting its point of maximum entropy at state 3, and that would make state 3 the limiting point. Is limiting point. Okay? So that's okay. So the question is like, how does this make any sense, right? So eventually it's a little confusing that you have the temperature start to increase as you add heat. Eventually it hits a maximum, and then as you continue to try to push heat in, you do manage to heat the flow more, but the temperature starts to drop. And so this is a little unintuitive. And the reason is the following. So unintuitive, that limiting point is not where T is maximized. But essentially, when adding heat, a portion of it goes into the enthalpy, and a portion goes into the kinetic energy. Right? And so you end up with H going up, the temperature going up, and the pressure going down, and the velocity going up, since G is a constant by mass conservation. Okay, and so eventually what happens is, since KE is proportional to V squared, it starts to take too much energy to increase it further, right? So the excess enthalpy is converted to kinetic energy. Okay, does that make sense? So you're trying to continue to increase the kinetic energy, and you can't, there's not enough heat to do so. So takes too much energy to increase excess enthalpy, which remember is proportional to the temperature, is converted to kinetic energy. Okay? So from 2 to 3, the enthalpy and the temperature go down, but the entropy itself and the speed continue to rise. Okay? So if we draw a Rayleigh line on an HS diagram, it looks like this. It goes up to reach a maximum enthalpy value, and then it turns downward like this and goes to the actual limiting point and then goes down like that. Okay? And it proceeds along this route. Say this is state 1, state 2, state 3, corresponding to what we have up here. Okay? If we drew, say, lines of constant pressure on this diagram, they would be kind of at this end, kind of like looking like this at this angle. Okay, so P const. Okay, so it's a similar structure to Fano, where you have this upper branch, and then you're going to have a lower branch below that limiting point too. So let's do our same table that we did before on the upper and lower branches. And as you might guess, I want to make it clear that this is not those don't connect there. On the lower branch, the flow is proceeding in the opposite direction towards the limiting point as well. So let's talk about what happens with the enthalpy, the density, the velocity, the pressure, and the stagnation pressure as well. So it's upper, lower. On the upper branch, the enthalpy actually goes up and down, right? Once it reaches point 2. The density is always decreasing, and so is the pressure, for example, and the velocity is always increasing. Okay, and then the stagnation pressure is always decreasing as well, because there's always entropy being produced. Okay, on the lower branch, the enthalpy only goes up, so you only raise temperature. And you have the density rising, the velocity going down, okay, and then the pressure going up, and then the stagnation pressure also going down, because again, that entropy change. Okay, so it's very similar structure to Fano flow, where you have sort of opposite things happening on both sides of the both branches of the line, and that's why, as you can see, we'll have a similar limiting point and kind of like choking behavior, but in this case it'll be like thermal choking. So of course, let's analyze that limiting point. So we know that P plus G squared over rho is equal to a constant on the line. That's how the line is defined. If we take the total differential of this, you end up with dP plus G squared times minus d rho over rho squared is equal to 0. And if we rearrange that, we end up with dP over d rho, again, dividing total differentials when we shouldn't be, is equal to G squared over rho squared equal to V squared. Okay, so that's true. So this is looks a little confusing because we have what looks like close to the definition of sonic velocity on the left being equal to the velocity all along the Rayleigh line, right? So is it true that anywhere on the Rayleigh line you have the sonic velocity? Well, remember the definition of sonic velocity is that derivative at constant entropy, right? So at limiting points, the change in entropy is 0, and so you can see that's where v becomes the sonic velocity. And so, much like with Fano flow, at the limiting point you have m equals 1. M equals 1, and then upper branch is subsonic, and lower branch is supersonic. Okay? So we also have that G is constant, right? And if we take the total differential of G, which is equal to rho times V, you get V d rho plus rho dV is equal to 0, which allows us to write d rho is equal to minus rho over V dV. Okay, if we sub that into dP is equal to V squared d rho, then we end up with dP is equal to minus rho V dV. Okay, then we'll sub that into our fundamental thermodynamic relation, the TdS relation, sub into TdS is equal to, keep lowercase s here, is equal to dH minus V dP, and that will be equal to dH minus dP over rho, yielding TdS equal to dH plus V dV. Okay? And then at the limiting point, the ds is 0. So you end up with 0 is equal to dH plus V dV. Well, that is the same as dH plus d of V squared divided by 2, and that's just d applied to the total enthalpy, or the stagnation enthalpy. And that means that the stagnation enthalpy is also maximized at the limit point. HT also max at limit point. Okay, and that makes sense, right? Makes sense because all we need to do is just look at the energy equation. We could have just looked at HT1 plus Q is equal to HT2. Well, HT2 is going to grow until you can't add heat anymore, and that's going to be your maximum stagnation enthalpy, right? But the question becomes, how does HT vary generally? Right, so usually this is, when we draw HT on these diagrams, it's just a straight line across the the diagram because the stagnation enthalpy is constant? Well, in this case, of course, it's not constant because we're adding heat. So I managed to zoom myself out quite a bit there. So let's go ahead and draw what that looks like, that stagnation enthalpy variation across the process. So we'll draw the HS diagram here. We'll draw our Rayleigh line. Okay, we'll label our limiting point and our point of maximum temperature. And then we'll also, in a moment, we'll draw, whoops. So this is subsonic, and this is supersonic. We'll also draw our lines of constant pressure in just a moment. So, but the stagnation curves look like the following. So we have, I'll draw them as, let's draw them as red lines. So we have one line that goes like this. Let's label this here. And then one line that's below that one, but corresponds to the subsonic branch, goes up to meet it. Okay, so that's the supersonic. And this is the subsonic. And then this is, of course, plotting HT on the same diagram. And let's draw some lines of constant pressure. They look like that. Okay, this is P const. All right, so at this point here, remember, we have our maximum enthalpy and temperature, but at this point here, we have our maximum stagnation enthalpy and our maximum entropy. And we also know that m is equal to 1 there. And that corresponds to this point of highest stagnation enthalpy up here in red. Okay? A quick little note. We know that the top branch of this HT is supersonic. Because dHT is equal to the change or the rate of change of heat addition, right? Which we know is equal to TdS because we're ignoring any sort of losses. And so we can think of the rate of change of H of T with respect to S, or as compared to the rate of change of S, is going to be equal to T. Okay, so at a given point in your entropy domain S, the subsonic branch has a higher temperature, and so it's going to have a higher slope. So that's why the subsonic branch lies below with a higher slope. So subsonic branch has higher T, which implies higher slope. That's why we drew those two red lines in that way. Okay, not the cleanest diagram I've ever drawn. Of course, the diagram in the textbook would be a lot more intelligible for you guys. Okay, so that's your introduction to Rayleigh Flow with all of the state diagrams, so you can get an idea of how those processes proceed. But now let's look at the working equations. Okay, so we'll start with momentum. We know that P plus GV is equal to a constant for Rayleigh flow. Which is the same as writing P plus rho V squared is equal to a constant. And then as per normal, when we write our working equations, we introduce the ideal gas law equation of state, as well as the Mach number, and then that allows us to rewrite these things. So in this case, we'll rewrite it as 1 plus P over RT, m squared gamma RT, the RT's cancel. This is going to be equal to some kind of constant. And so right away, we'll be able to rewrite the ratio between 2 points, or between 2 states, as 1 plus gamma m1 squared over 1 plus gamma m2 squared. Since that quantity stays constant, we can take the ratios in that way. And then we also have continuity, which tells us that rho v is constant, which is the same as Pm over square root of t is constant. And that leads us to T2 over T1 being equal to P2 squared M2 squared over P1 squared M1 squared, which we can use our previous, what we just wrote on for P2 over P1 to write 1 plus gamma M1 squared, quantity squared, M2 squared over 1 plus gamma M2 squared, quantity squared, M1 squared. Okay, so we have that working equation for temperature. Should also box this equation here. And then, of course, we should write down the ratio of densities between 2 states as well, which usually just flips some of the quotients here. 1 plus gamma M2 squared, that M2 squared times the quantity 1 plus gamma M1 squared. Okay? Pretty straightforward. Not create anything crazy going on there. If we want to talk about the stagnation quantities, we can just use our normal Tt is equal to T times this quantity 1 plus gamma minus 1 over 2 m squared. And that allows us to basically go straight to writing what the ratio of Tt2 is to Tt1. And I'll go ahead and slot in what we had for T2 over T1 above. And what you end up with is m2 squared times the quantity 1 plus gamma m1 squared times the quantity 1 plus gamma minus 1 over 2 m2 squared divided by m1 squared times the quantity 1 plus gamma m2 squared times the quantity 1 plus gamma minus 1 over 2 m1 squared. Okay, so that's that working equation. And then the same thing for pressure, stagnation pressure. We just have that same sort of interior there, but of course it's raised to the gamma over gamma minus 1. And so we can use that guy to write PT2 over PT1 is equal to 1 plus gamma m1 squared divided by 1 plus gamma m2 squared times this larger quantity 1 plus gamma minus 1 over 2 m2 squared over 1 plus gamma minus 1 over 2 m1 squared. That entire quantity raised to the power gamma over gamma minus 1. Okay, so there's our working equation for stagnation pressure. And so remember, we had this old relation that we kept on referring to, right? So what about this PT2 over PT1 being equal to e to the minus delta S over R? Right? So we've used that over and referred to that over and over again when we were developing the working equations to relate to be able to calculate the change in entropy, or to be able to calculate the stagnation pressure drop using the properties having calculated the change in entropy. But to remember, that was derived for an adiabatic scenario for delta Q equal to 0. Okay, so to get delta S, you need to use that Sacker tetrode or perfect gas equation for a change in entropy. Which is delta S, 1, 2, is equal to R times the natural log of rho 1 over rho 2 raised to the gamma over gamma minus 1 times the quantity P2 over P1 times the quantity, or raised to the 1 over gamma minus 1. Okay? So just keep that in mind. So we still need at least one downstream property to solve for the remainder of the downstream properties, right? But really all we'll do is we'll just use the total heat added. So use Q equal to Cp times TT2 minus TT1 to solve for downstream properties. And then this is implicitly assumed to be constant throughout the process, which can be particularly problematic when you have really high heat transfer rates. So not the most realistic assumption for sure. Okay. Cool. So you'll often know, how many joules your burner is adding to the system per unit of mass flow rate. And that'll allow you to get the total the stagnation temperature before and after a burner or whatever process you're interested in. And you can find all those other process changes using those working equations that we just wrote down. Okay, so like with Fano flow, we need to define a new reference state called the Rayleigh star reference. And it's same sort of song and dance as before. We are just going to define it as the state that you reach, and we'll call it star R as well. Star R, state reached at m equals 1 on a Rayleigh line. Okay, straightforward, same stuff what we've been doing with. The interesting thing here is like, if you draw this, you can't really draw this using like the hypothetical ducts, idea that we were drawing before, because to move along a Rayleigh line here, you actually add heat. You don't travel down the duct, right? So like moving between, M1 and M2 here, you have some sort of heat that's entering the system. And then, you could say that it's like hypothetical longer section of duct, but where you have, more heat being added, and eventually you reach M star R equal 1. But, the length of the duct is truly hypothetical in this case. But just like Fano, you can use this reference state to solve a bunch of different problems. Your P over P star R, all those relationships, etc. Those Rayleigh flow relations where we plug in M equals 1 is the working equations we just talked about to derive. Those are all in Appendix J. Okay, of Zucker and Govar's. So those, if you want to use those tables. Okay, so let's do some examples. Using this reference state. So the reference state idea, I should say. So let's draw a duct. And let's say we're going from a state 1 to a state 2 on the right. And we have some sort of heat transfer crossing the boundary, okay, Q. But we want to know what the direction is. Is it in or out? And the flow is proceeding from 1 to 2. We know that M1 is equal to 1.5. We know that P1 is equal to 10 psi absolute. We know that M2 is equal to 3. And P2 is equal to question mark. We don't know what that is. So then the question is, okay, what direction is the heat transfer going here? And so we can go back up to look at our Rayleigh line here. We know that the Mach number at the beginning is supersonic, so we're on the lower branch, but M went up. Okay, so if we're on the lower branch and V is going up, that means that heat must be being subtracted or leaving the system. So we're actually progressing on the Rayleigh line here, just to draw this very quickly. We're actually progressing in this direction on the Rayleigh line, backwards, so we're subtracting heat. Okay, so we know that this guy is telling us that heat is being subtracted, right? And we can look at the tables to get P2. So P2 over P star R, and then P star R over P1. Both of those values you can get from the tables for using the Mach numbers, and then we know what P1 is. And so we know that we're going to get 3.05 psi as our answer. M2 greater than M1. That's why heat is being subtracted. Okay, so let's look at another. That's a very simple example. Let's look at another one. That's another thing that's interesting about Rayleigh flow is that because heat is something that can be added or pulled from the system, you can move along both directions on the process diagram. Whereas with Fano flow, it's just friction. So as you proceed along the duct, you're only moving in one direction. So let's look at this example where we have heat being added to a duct. And we'll have a state 1 and a state 2, heat being added. Okay, T1 is going to be 400 Rankine. P1 is going to be 10 psi. And V1 is going to be 402 feet per second. N2 is 1.0 sonic. And then we want to know what P2 is. And we also want to know how much heat is being added. Okay, so first off, we can calculate M1 because we have T1 and V1, right? So that's going to be V1 over the square root of gamma R T1. So that equals 0.41. And then 4.0. And so using Appendix J, that tells us that T1 over T star R, T star R, is equal to 0.5465. Okay. We also know, using M1 and T1, that TT1 is equal to 413 degrees Rankine. Okay. And in Appendix J, we also found that P1 over P star R is equal to 1.9428. Okay, so we have these two guys, this TT1 and T star R, and so we put those together and we'll end up with, we can get TT2, and we know in this case, since M2 is equal to 1, that TT2 is TT star R. So that is what the stagnation temperature is at the star R reference state. And so that's equal to 756 degrees Rankine. Okay? And then this guy here can tell us that P2, which is P star R, is equal to 5.15 PSI. Okay? So that's our pressure at the exit. And then we have, to get our heat transfer, the reason why I calculated TT2 is because our heat transfer is equal to CP times TT2 minus TT1, which in this case is 82.3 British thermal units per pound mass, using the heat capacity of air. Okay? That's how much heat we would have to add to reach the star R reference state in this case. Okay, and so let's conclude with a brief discussion, just like kind of like what we did with Fan of Flow. We'll first have a really short discussion about shocks, and then we'll talk about thermal choking. So on a Fano line, shocks jump between points of equivalent P plus rho V squared. But that's constant everywhere on a Rayleigh line. So, but normally HT has to be conserved across a shock. So the stagnation enthalpy. So on a Rayleigh line, you jump to a point on the subsonic branch with the same HT. So the best way to see this is to draw that diagram that we drew before, where we were plotting HT as well as the Rayleigh line. This is a little tricky to draw, so hopefully it's not like totally impossible to understand. But I'll start with, let's say we do these guys first. Okay, so those are our lines of constant HT. Or not constant HT. In fact, those are our lines of where HT is evolving on this HS diagram, right? And then we will draw the Rayleigh line below. Okay, and let's, that was terrible. Let's do it this way. It's better. And then let's imagine that we're starting here at state 1, okay? And then we proceed a little bit to state 2. And so state 2 brings us up, remember, on the top branch here. Okay, so this is HT2, okay? And then what we have to do is we have to jump across to the subsonic branch with a same value, HT3 being equal to HT2. And then that corresponds down here to this state here. So this will be state 3. So the shock process proceeds between state 2 and 3 in that way. And then you would keep, progressing toward the limiting point over here to state 4. Okay, so that's the way the shocks occur for Rayleigh. So Rayleigh jump to a point on subsonic branch with same total enthalpy value. Okay, and that's because, like we said in the Fano flow lecture, there's those 3 quantities that you want that must be conserved across the shock: the total, the stagnation enthalpy, that P plus rho v squared quantity, which in this case defines the Fano line, the Rayleigh line, and so it's always true. And we need to conserve mass flow rate across the shock. So we're already conserving mass flow rate, and we're already conserving the P plus V rho v squared on a Rayleigh line. But we don't, since we have heat transfer, we're not always conserving total stagnation enthalpy. So we need to jump to a point with the same value. So that's what's happening in this diagram. And then we'll also say something very quickly about thermal choking. It's almost exactly the same deal as Fano, so we don't really have to say too much about it. So it's like Fano flow. You get a new condition with a lower mass flow rate or mass velocity g if or is needed to allow for more heat transfer beyond the limiting point. Okay, and then the diagram actually looks basically the same. So if you draw that HS diagram where you have your original thing that goes from 2 to a limiting point at 3, and you want to increase more heat, say you started up here at 1, instead you're going to go to 2 prime, and you're going to jump onto a Fano line that has a lower G. And 3 will be like here, but you'll be able to proceed further to a state 4 here and add more heat at a lower flow rate. Okay, and so that would be like the new Fano line that you're now on. All right, so that is the end of Rayleigh flow. Apologies if it was almost a little too similar to the Fano flow and kind of a dry lecture, but it is important that you know Rayleigh flow, because that is sort of the dominant paradigm through which you understand what's going on in a burner when heat is being added to your flow in a propulsion system. And so, to be honest, the biggest takeaway is you just have to remember that the stagnation temperature is changing, but occasionally you have to go and look at these Rayleigh flow temp tables to calculate what's happening across a burner. So it's important that you know these things. But otherwise, the next lecture, we're actually going to take a little bit of a detour to hypersonics, to look at the hypersonic limit. And then after that, we're going to dive straight into propulsion systems. Maybe later on, not this recording iteration, but later on I might inject a lecture to where we combine some of these effects like Fano and Rayleigh and variable area at the same time. But for now, we'll go from hypersonic straight to propulsion systems. So yeah, should be interesting. The propulsion system stuff I think is like is the most fun stuff to learn about. It's also the most challenging. So you can look forward to that. Thanks for listening, and I'll see you next time.